Welcome to the Explainer. I am so excited to be your guide today as we dive into a really fascinating topic, the Universal Rulebook of Solutions. Think about it. Pure substances are actually incredibly rare in our day-to-day lives. Almost every process in our bodies and the materials we use all the time, they occur in some kind of chemical mixture. So today, we're going to enthusiastically unpack both the microscopic building blocks and the macroscopic physical laws that govern these mixtures. By the end of this, I promise you're going to see the physical world in a completely different, highly structured way.
All right, here is our mental roadmap for this explainer. First up, types and concentration units. 2, Henry's Law in action. 3, Raoult's Law and vapor pressure. 4, ideal versus non-ideal solutions. 5, the 4 colligative properties. And finally, number 6, the Van Hoff factor. Let's get right into it.
Section 1. Types and concentration units. The microscopic foundations.
So, what exactly is a solution? Well, it's not just random things thrown together in a beaker. A true solution is a strictly homogeneous mixture of 2 or more components. And what that means is its composition and its properties are completely uniform throughout the entire thing. Typically, the component that you have the most of is the solvent. You can think of the solvent as the boss. It's the one that determines the actual physical state of the solution. And then anything else dissolved within it, well, those are your solutes.
Now, normally when we hear the word solution, most of us immediately picture, a powder dissolving in a liquid. But solutions can actually exist in all 3 physical states. Sure, you can have a gaseous solution, like the oxygen and nitrogen mixture we're all breathing right now. You've got your classic liquid solutions, like ethanol dissolved in water, but you can even have solid solutions. A perfect example of a solid solution is copper dissolved completely uniformly in gold.
When it comes to describing these mixtures, using qualitative words like dilute or concentrated just kind of leads to a lot of confusion. I mean, is my idea of dilute exactly the same as yours? Probably not. Because of this, scientists rely on 7 specific quantitative mathematical tools to express concentration. Things like mass percentage are absolutely huge in industrial applications, while molarity and molality, those are the go-to tools you'll see used in a chemistry lab.
And this next number brilliantly illustrates exactly why we need so many different units. 5.8 parts per million. That is a staggeringly tiny number. Yet, this exact trace amount, literally just 5.8 grams of dissolved oxygen for every million grams of seawater, is the critical concentration that keeps all marine life on Earth alive. So, when a solute is present in just trace quantities like that, parts per million is absolutely the perfect tool for the job.
Section 2. Henry's Law in action. Pressure and solubility.
To really understand this, let's pose a real-world question. Why do scuba divers get that terrifying, painful condition known as the bends? Well, the answer lies entirely in how gases behave under pressure, and it leads us straight to our first major physical law of this explainer.
The mystery of the bends is totally solved by Henry's Law. It states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid. Basically, think of it as the soda rule. High pressure literally forces gas molecules into the solvent. So for a scuba diver who is breathing air at a really high pressure underwater, atmospheric gases are forced to dissolve right into their bloodstream. If they swim to the surface way too quickly, that pressure suddenly drops, and all those dissolved gases rapidly escape back into their vapor phase, which forms incredibly dangerous bubbles in their blood capillaries.
Section 3. Raoult's Law and vapor pressure.
Way back in 1886, a French chemist named François-Martin Raoult discovered a really fundamental relationship for these mixtures. Raoult's law states that for a solution of volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. To put it simply, the more of a volatile liquid you have in your mixture, the more it contributes to the vapor hovering right above the solution.
Now, the crucial thing here is to compare these 2 foundational laws side by side. Notice how structurally identical their formulas are. In both cases, the partial pressure equals a constant multiplied by the mole fraction. Raoult's law is actually just a very special case of Henry's law. The only real difference is that Henry's law uses this experimental constant Kh, while in Raoult's law, that constant simply becomes the natural vapor pressure of the pure solvent itself.
Section 4. Ideal versus non-ideal solutions.
So we generally split solutions into 2 camps. First, we have ideal solutions. These are the strict rule followers. They obey Raoult's law perfectly across all concentrations. If you mix liquid A and liquid B, absolutely no heat is absorbed or released, and the final volume is exactly the sum of the two original parts. This happens when the intermolecular interactions between A and B are perfectly balanced and equal to what they were in the pure substances. Non-ideal solutions, on the other hand, deviate from the math. Introducing a new substance completely disrupts those existing intermolecular forces, which changes how easily the molecules can escape into vapor.
Let's break down those non-ideal deviations. When you mix ethanol and acetone, the new molecules actually get in the way and break existing hydrogen bonds. So the new A-B interaction is weaker. Because they're holding on to each other a lot less tightly, it's easier for molecules to escape. This causes a positive deviation, where the vapor pressure spikes higher than what Raoult predicted. Conversely, if you mix phenol and aniline, they form new, surprisingly strong hydrogen bonds. They hold on tight. This drops the vapor pressure, creating a negative deviation. And at extreme levels, these deviations can even create azeotropes, which are mixtures like nitric acid and water that end up boiling at a completely fixed, constant temperature.
Section 5. The 4 colligative properties. These macroscopic properties are called colligative properties. The term actually comes from Latin, meaning bound together. Now here is the absolute unbreakable golden rule you need to remember. Colligative properties depend entirely on the number of solute particles relative to the total, and they do not care at all about the chemical identity of those particles. Nature simply counts the pieces. It really doesn't care what the pieces are actually made of.
There are 4 interconnected colligative properties. When you add a non-volatile solute to a solvent, it takes up space at the surface of the liquid, which physically blocks solvent molecules from escaping. This causes a relative lowering of vapor pressure. Because the vapor pressure is lower, you now have to heat the solution more to make it boil. That's your elevation of boiling point. It also disrupts the ability of the solvent to form a solid lattice, meaning it depresses the freezing point. By the way, this is exactly why adding antifreeze to a car engine prevents the water inside from freezing in the dead of winter. And finally, we have osmotic pressure.
Osmotic pressure is so critical it really deserves its own spotlight. The formula is beautifully simple. Osmotic pressure, which we denote by P or sometimes pi, equals C times R times T. C is the molarity of the solution. This tells us that osmotic pressure is directly proportional to the concentration of the solution at a given temperature. This specific colligative property is literally the fundamental mechanism that drives water and nutrient absorption in the roots of plants, and it dictates the delicate balance of blood plasma in your very own veins.
Section 6. The Van Hoff factor.
Okay, remember our golden rule? Colligative properties depend on the number of particles. But what happens if you dissolve salt and water? A single salt molecule splits or dissociates into 2 separate ions. Suddenly, you have twice as many particles as you originally calculated. In other cases, molecules might actually clump together or associate. This is where the Van Hoff factor, represented by the letter I, comes in. It's our essential correction tool. It's a multiplier that we inject right into our colligative property formulas to fix our math, ensuring that our calculated values perfectly match what we observe in real-world experiments.
We've scaled all the way from microscopic mole fractions to the macroscopic forces of osmotic pressure. So I'll leave you with this provocative thought. As you go about your day, from the pressurized, Henry's Law-abiding carbonation in the soda sitting in your fridge to the life-sustaining osmotic pressure balancing the plasma in your veins, which universal solution rule is actively working to keep your physical world in balance right now? Thank you so much for joining me on this explainer, and as always, stay curious.